In this presentation we are going to look at hypothesis testing, particularly for small samples. Now suppose a quality control laboratory are testing the lifespan of a brand of ultraviolet tubes, and the lifespan of a sample of 10, let's pick up that point first off, that this is a small sample and that n is equal to 10. The lifespans were measured, and the average lifespan of this sample was found to be 8,800. And there we have it there. That is our point estimate. So the standard deviation of the lifetimes were of the furthest of the sample were found to be 500 hours. There's a little typo there. It should be lifespans or lifetimes. So S is equal to 500 hours, and it's also assumed that the operating lifetime is normally distributed, which is an important point. Now, the average tube life for this brand is claimed by the manufacturer to be 9,000 hours. So, test this claim at a 5% significance level. So that's our significance level, alpha, 0.05, which is to say 5%. Okay, so we're going to use that later on. Now, the alternative hypothesis is that the mean is not equal to 9,000 hours. That means the null is equal to 9,000. They have to express direct opposite statements, direct contradictions. So let's write that down now. Formally write out the null and alternative hypothesis. Let's just make an important point here. This is something that trips a lot of people up. You are making a claim about the population parameter, in this case the population mean. You're not making any statements about the sample. You're using the sample data to base a judgment on, but you're not making any statements about the sample. So you always use population parameters such as mean, mean, and proportion or something like that. So the null hypothesis mu is equal to 9,000 hours. Let's write a little description. Average lifespan is 9,000 hours. The alternative hypothesis is that it's not equal to 9,000 hours. So that's straightforward enough. So just a quick remark actually, this is a two-tailed procedure, and usually we write k as the number of tails. So k either is one-tailed or two-tailed. In this case it is a two-tailed procedure. How do I know? Because we have not equal to here and equal to here. So when we have that pairing of symbols, that means we have a two-tailed test. Okay, so let's compute the test statistic, TS. There's lots of ways of writing this down actually, but I just use TS for the sake of simplicity because I do. Anyway, so x bar minus mu, that's the point estimate, minus the null, the expected value under the null hypothesis, or whatever the average value is claimed by the null hypothesis. And in this case it is 8,800 minus 9,000, so this part here, the numerator part, works out to be minus 200. This part here is the standard error, and we also have to calculate this. And how do we calculate that? We would actually go to the formula at the back of the exam paper if it's there. In some modules though you might have to learn them all off by heart, and there are quite a few of them. So anyway, it is sigma divided by the square root of n. Now, standard error is determined from formulas unless you're very unlucky. We use the sample standard deviation S as an estimate. Now that's an important point here. S as an estimate for sigma, because sigma is unknown. So where we had sigma previously, now we're just writing in S. S divided by the square root of n. That was 500 divided by the sample size, the square root of the sample size, square root of 10. And two decimal places, that works out to be 158.11. Test statistic, therefore, is minus 200 divided by 158.11. So our test statistic works out to be minus 1.265. Now, sometimes you will get a negative test statistic. That is not really important. Nothing's going wrong if you get a negative test statistic. Now, what we're going to do now here is use the student t-distribution. We have a small sample, so we're going to use the student t-distribution. Now, the critical value is determined with using the following factors here. Alpha is 0.05. Number of tails is 2. It's a small sample, n equals 10, and therefore the degrees of freedom, df, is n minus 1, and in this case it's going to be 9. Now, there is quite a few different types of statistical tables, and each would be formulated a different way. So if I was to sort of discuss one way, it might mislead people who are using different tables. So I've chosen to avoid how to explicitly show how to get the critical value, other than indicate the key values that are required to find it. So suffice to say, you should end up with a critical value of 2.262. So that is our critical value. So the last part is the decision rule. Is the absolute value of the test statistic greater than the critical value? Is absolute value of TS greater than CV? Well, the absolute value of the test statistic is minus 1.265, and that is equal to 1.265. Just disregard the sign. Is that the case? No. So we fail to reject the null hypothesis. There is not enough evidence that the mean lifespan for this brand is not 9,000 hours. We just seem to have got just quite a few short lifespans. Otherwise, we have made a type 2 error. Anyway, that is the end of this